physics teacher to discuss some very interesting topics of electrostatics. Till now you have studied electrostatic force or Coulomb's force, which is a very important law in electrostatics. I think the whole electrostatics is based on this principle. Today we will understand the electric potential. Electric potential is the amount of work done in moving a unit positive charge from infinity to a point in an electric field against the electrostatic forces. Mathematically, electric potential is written as work done by charge, and similarly it is expressed as V is equal to W by Q. It is written as so if we suppose Q amount of if we suppose W amount of work is done moving a charge Q unit, yes, this similarly V is equal to W by Q is written as if in moving Q charge or plus Q charge W amount of work is done, then in moving unit positive charge it will become W by Q. So it is written as similarly V is equal to W by Q. Clear? So this is electric potential. It is a scalar quantity and its SI unit is volt. Its dimension is ml square p to the power minus q and A inverse. As V is equal to W by Q, so I have written here dimensions of work and dimension of charge as charge is equal to I, which is I is equal to Q by P, rate of current, as current is defined as rate of flow of charge. So I is equal to P by T and P is equal to IT, and hence dimensions of charge is here AT. I have put here AT, and this is equal to, this has become ml square T to the power minus Q A inverse. So this is the dimension of electric potential. Clear? Next, we understand potential difference. The two terms electric potential and potential difference mathematically has the same form, but there is difference in physics. Electric potential is the amount of work done in moving a unit positive charge from infinity to a point in an electric field against the electrostatic force. But potential difference is the amount of work done in moving a unit positive charge from one point to another in an electric field against the electrostatic forces. As shown in this diagram, here Q is the source charge and Q naught is a test charge which has to be moved from the point A to B against the electrostatic force of this source charge Q. It is clear? So Q is a source charge, point source charge located at the point O. Q naught is a test charge. Actually this test charge, it has some also electric field, but its electric field is negligible in comparison with the electric field of this source charge. So we have not to consider the electric field of this test charge Q naught. Q naught is a test charge which is moved from the point A to B, and WAB is the work done in moving this test charge Q naught from the point A to B against the electrostatic force exerted by the source charge plus Q. Then the potential difference between the points A and B will be given by you can write here potential difference between the points A and B. Then we continue here from here to here. Then the PD between the points A and B is WAB is equal to VB minus VA upon Q naught. This is the potential difference between the point A and B. Sorry. You can write like this: V is equal to VB minus VA is equal to WAB upon Q naught. This is the potential difference between the points A and B. Potential difference is also a scalar quantity and its unit is also volt, and it has the same dimension as the electric potential. Let us define 1 volt of electric potential or potential 1 volt of electric potential or electric potential of 1 volt and 1 potential difference of 1 volt. Electric potential of 1 volt. Since V is equal to W upon Q, so if W is equal to 1 joule and Q is equal to 1 coulomb, then what we will get? Then we will get electric potential V is equal to 1 upon 1 is equal to 1 volt. Hence, in this way, 1 volt of electric potential is defined, or the electric potential at a point in an electric field is said to be 1 volt if 1 joule of work has to be done in moving a positive charge of 1 coulomb from infinity to that point against the electrostatic forces. Similarly, we can define potential difference of 1 volt. Potential difference of 1 volt the potential difference between 2 points in an electric field is said to be 1 volt if 1 joule of work has to be done in moving a positive charge of 1 coulomb from one point to another against the electrostatic forces. Hence, 1 volt will be equal to 1 joule per coulomb. 1 volt will be equal to 1 joule per coulomb or 1 Newton meter per coulomb. This is potential difference of 1 volt and potential electric potential of 1 volt. Next, we determine the electric potential due to a point charge. As shown in the diagram or in the joining figure, here plus Q is a positive point charge placed at the point O or origin O. Here plus Q naught is a test charge placed at point A at a distance x from the origin O. P, here the point P is a point at a distance r from the point charge plus Q at which the required electric potential has to be calculated. It means P is the point in the electric field of this source charge or point charge at which we have to calculate or determine the electric potential. From Coulomb's law, we can write here next. From Coulomb's law of electrostatic force, we can find the electrostatic force exerted by this point charge on this test charge Q naught. So we can write here by Coulomb's law the electrostatic force, Coulomb's law, by Coulomb's law, the electrostatic force acting on the test charge, Q naught due to the point charge Q is F is equal to 1 by 4 pi epsilon naught into Q naught divided by the distance from this point charge to Q naught. It will be equal to x square. As we know from Coulomb's law that the electrostatic force between two point charges is directly proportional to the product of the magnitude of the two charges and inversely proportional to the square of distance between them. So according to the Coulomb's law, we have written here F is equal to 1 upon 4 pi epsilon naught into Q1 Q naught by x square. Now if we take here the small distance between A and B, the displacement between A and B is dx. Then we can calculate the small work done the small work done in moving the test charge Q naught from A to B. We can write the small work done in moving the test charge Q naught from A to B, through a small distance dx, through a small displacement dx against the
इसी को छू दीजिएगा फिर और रोकने बोले तो उसी को ठीक है
electrostatic
वहाँ लिखवा लीजिए
force is F dot dx and it will be equal to F dx cos 180 degree, as both here force and displacement, the direction of force is in this way and the direction of displacement is in this way. So both force and displacement are in opposite direction. So we have taken here the angle between force and displacement 180 degree. So we get work done, small work done in moving the test charge Q naught from, test charge Q naught from the point A to B is equal to F minus F dx, since cos 180 degree is equal to minus 1. Cos 180 degree is equal to minus 1. So this is the small work done in moving the test charge Q naught from the point A to B. Sure. If you consider the question 1 and this 2, then we can calculate the total work done in moving the test charge Q naught. Therefore, the total work done in moving the test charge Q naught from the point test charge Q naught from infinity to the point from infinity to the point P is given by here this will be small work done. A small work done will be dW. and the total work done will be equal to W integration of dW from is equal to integration of minus f dx from infinity to the point r. Now we can put the value of F force and displacement df dx. We can put here the value of force from 1. This will be equal to minus integration from infinity to the point r, and we put here the value of force from 1 by 4 pi epsilon naught into q naught divided by x square dx. This is a constant term. This whole q naught upon 4 pi epsilon naught is a constant term. So we can take common. This will be equal to minus q naught upon 4 pi epsilon naught integration from infinity to r 1 upon x square dx. This will be equal to minus q naught 4 pi epsilon naught into integration from infinity to the point 2r x inverse x minus 2 x to the power minus 2 dx. Now with this remove this integration, applying the formula. Since integration of x to the power n x n dx is equal to x to the power n plus 1 upon n plus 1. According to this integration formula, we apply here this formula and we get the result. Work done is equal to minus q naught upon 4 pi epsilon naught. It will be equal to x inverse upon minus 1. And the limit, we place the limit here infinity to r. This will become work done is equal to q naught upon 4 pi epsilon naught. It will become positive when minus this minus sign, this minus and minus will become plus, and it will be equal to q naught upon 4 pi epsilon naught 1 upon x infinity to r, and this will be equal to q naught by 4 pi epsilon naught into 1 upon r minus 1 upon infinity, as 1 by infinity is equal to 0. So this will be equal to work done is equal to q naught upon 4 pi epsilon naught into 1 by r, or this implies we can write work done is equal to 1 by 4 pi epsilon naught into q naught by r. This we consider question number 3. This is the amount of work done in moving the test charge q naught from infinity to the point P. So the electric potential is defined as the amount of work done in moving a unit positive charge. Here we have taken q test charge q naught from infinity to the point A. So if we take unit test charge q naught, then it will become, so the electric potential at the point P, V is equal to q naught, and it will become q naught and q naught will be cancelled out, then it will be equal to 1 by 4 pi epsilon naught into q by I. This is the required expression for the electric potential due to a point charge. Question 4. Let us calculate the electric potential. Electric potential due to a group of point charges. Previously we have calculated the electric potential due to a point charge. Here we will calculate the electric potential due to a group of point charge or system of charges. So let us draw a diagram. Here is the point P, and here is the point charge Q1 at a distance R1 from the point P. Here is the point charge Q2 at a distance R2 from the point P. Here is the point charge Q3 at a distance R3 from the point P, and this we consider point charge Q4 at a distance at a distance R4 from the point P, and this one is point charge Qn at a distance Rn. Even we can name the figure electric potential due to electric potential at a point electric potential at a point due to electric potential at a point due to a system of n point charges. The figure is clear. Q1, Q2, Q3, Q4 and Qn are n point charges at the distances r1, r2, r3, r4 and rn respectively from the point P. Then the electric potential we can write here as shown in the adjoining figure. Consider Q1, Q2, Q3 Qn point charges at distances r1, r2, r3 rn respectively from the point P. Then electric potential at the point P due to the point charge Q1 is, as we have determined the expression for electric potential, V is equal to 1 by 4 pi epsilon naught into Q by R. So here the electric potential at the point P due to the charge Q1 will be equal to V1 is equal to 1 by 4 pi epsilon naught into, here the charge is Q1, so it will be Q1 at the distances R1, so it will be R1. This is the electric potential at the point P due to the point charge Q1. Similarly, we can find the electric potential at the point P due to other charges like similarly electric potential due to electric potential at the point P due to other charges V2 is equal to 1 by 4 pi epsilon naught into Q2 by R2. V3 is equal to 1 by 4 pi epsilon naught into Q3 by R3 and so on. We can write and so on. Vn is equal to 1 by 4 pi epsilon naught into Qn by Rn. As electric potential is a scalar quantity, the total potential at the point P will be equal to the algebraic sum of all the indivisible potentials at the point P. Proceed here. As the electric potential is a scalar quantity, so the total electric potential at point P will be equal to the algebraic sum of all the indivisible potentials, sum of all the individual potentials at the point P. That is, it will be equal to, that is, V is equal to V1 plus V2 plus V3 dot 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 plus Vn. If we put the value of this V1, V2, V3, we will get the common term 1 by 4 pi epsilon naught into Q1 by R1 plus Q2 by R2 plus Q3 by R3 plus dot 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 plus Qn by Rn. And this can be written as V is equal to 1 by 4 pi epsilon naught sigma from I is equal to 1 to n Qi upon Ri. This is the electric potential due to a group of point charges.
चलिए
Let us see some numericals about this electric potential. How can we solve the numericals using the formula of electric potential? We can note down the problem. A total electric charge of 8, a total electric charge of 8 nanocoulomb is distributed uniformly distributed uniformly over the surface of a metal sphere over the surface of a metal sphere with a radius of 27 centimeter. If the potential is zero at a point at infinity, if the potential is zero at a point at infinity, find the value of the potential. Find the value of the potential at the following distances. At the following distances from the center of the sphere. Center of the sphere. A, B, C. In A, first is 52 centimeter, 20 centimeter, and 9 centimeter. 52 centimeter, 20 centimeter, and 9 centimeter. Let us see how can we solve. Here the amount of charge is given 8 Nc. Q is given. You can write Q is equal to 8 Nc. We convert this into coulomb. 8 into 10 to the power minus 9 coulomb. And potential is zero at a point at infinity. V infinity is zero. Then here the center of the sphere is also given. R is given. Center of the sphere, metallic sphere, center of metallic sphere is given 20 centimeter, 27 centimeter. So for first, this 52 centimeter is greater than R. We have to calculate VR. It will be equal to 1 upon 4 pi epsilon naught into Q. The amount of charge is given here 8 into 10 to the power minus 9 upon distance is 52 centimeter. We convert this into SI unit. It will be equal to 0.52 meter. We put the value of this constant 9 into 10 to the power 9 9 into 10 to the power 9 into 8 into 10 to the power minus 9 divided by 0.52. By solving this, we can get this 10 to the power 9 and 10 to the power minus 9 will be cancelled out, and it will become 9 into 72 divided by 52 and this. You cancel this. 13 4 jam 52 and 18 4 jam 72. It will become 18 by 13 into 100, and it will be equal to 1.3. It will be equal to 1.3 into 10 to the 10 square volt. Similarly, we can calculate the electric potential at 20 centimeter and 9 centimeter. In this class, we have understood Coulomb's law. Electrostatic force F is equal to K Q1 into Q2 by R square, as this is a very important law proposed by French military engineer and physicist in 1785. This law, this Coulomb's law, was given by the French physicist, engineer, French military engineer and physicist in 1785. And Coulomb's force is also known as the electrostatic force between elementary charged particles or objects at rest. It means this force, this Coulomb's force or electrostatic force, exists only when the charged particles or charged bodies are at rest. Next, electric potential. We have determined electric potential V is equal to, expression for V is equal to 1 upon 4 pi epsilon. This is a constant quantity as K, and value of K is given as is equal to 9 into 10 to the power 9 Newton meter square per Coulomb square. Value of this constant has been calculated experimentally, and it is equal to 9 into 10 to the power 9 Newton meter square per Coulomb square. We have also understood potential difference between electric potential and potential difference. The two terms are exactly the similar, both has same units and dimension, both has same mathematical formula, but the difference between the two is that the electric potential is defined as the amount of work done in moving a unit positive charge from infinity to a point in an electric field against the electrostatic forces. But this potential difference is the amount of work done in moving a unit positive charge from one point to another in an electric field against the electrostatic forces. So the difference between the two is clear. Next, we have also understood the electric potential of 1 volt potential difference of 1 volt, which is defined, or electric potential of 1 volt is defined as the amount of work done when 1 joule of work done, 1 joule of work has to be done in moving a positive charge of 1 coulomb from infinity to a point in an electric field against electrostatic forces. Similarly, potential difference of 1 volt, it is the when 1 joule of work is done in moving a positive charge of 1 coulomb from one point to another in a point against electrostatic forces. Next, we have calculated the electric potential due to a point charge. This expression for this is electric potential due to a point charge. It has the expression V is equal to 1 by 4 pi epsilon naught into Q by R. And next, we have calculated the electric potential due to a group of n point charges or system of n point charges. Next class, we will find the electric potential due to a dipole. Okay students, your task is to study these topics and understand clearly and to solve the given numerical problem. 2 numerical problems I have given. In next class we will discuss the topic and then we will start the next topic, electric potential. We will calculate electric potential due to dipole. A dipole, what is a dipole? Previously we have studied this dipole. Dipole is it consists of 2 equal and opposite point charges. Dipole consists of 2 equal and opposite point charges separated by some distance. Suppose here is minus q charge, here is plus q charge, and separation between them is L, 2L, then it is a dipole. So dipole consists of 2 equal and opposite point charges separated by some distance. So next class we will calculate the electric potential due to a dipole in axial position and at equatorial position. Axial position is in this axis and equatorial is a line passing from the center of the dipole. Axial position is the line going from its axis and equatorial line, a line going from its center. So in the 2 cases we will calculate the electric potential due to a dipole in axial position and in equatorial position. In